Alkynes, Chapter 9. Objectives: 1. Sources and uses. 2. Nomenclature. 3. Alkyne reactions. 4. Synthesis of alkynes. And 5. Synthetic strategies. Your goals. By the end of the chapter, you should be able to indicate sources and uses of alkynes, name and draw alkynes, predict alkyne reactions and synthesis, predict reagents needed from starting substrate to target, write mechanisms, propose viable synthetic routes. 1. Sources and uses. Alkynes are molecules that possess at least one C triple bond C. Each carbon of the triple bond is sp hybridized and has a linear electron and molecular geometry. There are 2 unhybridized p orbitals remaining for each carbon of a triple bond that result in the formation of pi bonds, and we're going to have 1 sigma between the 2 carbons of the triple bond and 2 pi bonds. Acetylene is the simplest type of alkyne. It is used in blow torches and in welding, and it's also a precursor for the synthesis of more complex alkynes. There's more than 1,000 different alkyne natural products that have been isolated. An example of a synthetic alkyne is ethinyl estradiol. It is the active ingredient in many birth control pills. 2. Nomenclature. Alkynes are named using the same procedure we saw earlier for alkanes, but with minor modifications. 1. Identify the parent chain, which should include the C triple bond C. 2. Identify and name the substituents. 3. Assign a locant and prefix if necessary to each substituent, giving the C triple bond C carbons the lowest numbers possible. 4. List the number of substituents before the parent name in alphabetical order. We ignore prefixes except for iso when we order them alphabetically. 5. The C triple bond C locant is placed either just before the parent name or just before the -ine suffix. For example, let's name this compound here. This compound has a 7-carbon parent chain, and the triple bond is between carbons 2 and 3, so we're going to call this 2-heptyne or hep2-ine. We have branches on carbons 5 and 6. The branches are methyl groups, so we're going to combine them and use the prefix tri, or 5,5,6 trimethyl 2-heptyne, or we can put it in as an infix, 5,5,6 trimethyl hep2-ine. There's also common names that are derived from acetylene. For example, methylacetylene, diisopropyl-acetylene, phenylpropyl-acetylene. Alkynes can also be classified as terminal or internal. Terminal alkynes represent any alkyne that has a CH where the C is part of a triple bond. Internal alkynes have carbons of a triple bond that are connected directly to R groups. 3. Alkyne reactions. Terminal alkynes. Recall that terminal alkynes have a lower pKa, i.e. more acidic, than other hydrocarbons. For example, the pKa of ethane is 50, ethylene 44, acetylene 25. It's more acidic. Acetylene is 19 pKa units more acidic than ethylene, which is 10 to the 19 times stronger. Terminal and internal alkynes. Recall that pi bonds may undergo reaction. Acidity. Acetylene can be deprotonated by a strong base to form the conjugate base, the acetylite ion. So here is the base reacting with the acid, resulting in the conjugate base of this acid, the ion. Recall ARIO, atom, resonance, induction, and orbital to explain why acetylene is a stronger acid than ethylene, which is stronger than ethane. The acetylite ion is more stable because the lone pair occupies an sp orbital and has more s character. We saw that the sp3 orbital is less stable. The more stable species is going to be in the sp hybridized orbital, which has more % s character. Suitable bases. A base's conjugate acid, pKa, must be greater than 25 for it to be able to deprotonate a terminal alkyne. Any terminal alkyne can be deprotonated by a suitable base. Sodium amide is often used as a base, but others can be used as well. Any of these bases will deprotonate a terminal alkyne, while these will not be able to deprotonate a terminal alkyne. For example, if we have that amide species, it is going to be the stronger base. It will remove H plus from the stronger acid, resulting in a weaker acid and a weaker base. If we work with sodium hydroxide, hydroxide is actually a weaker base. It would produce a stronger base, the acetylide ion, meaning that equilibrium would not favor these products, equilibrium would favor the reactants. So hydroxide is not a suitable base. Let's consider the reduction of alkynes. Catalytic hydrogenation, an alkyne can be converted to an alkane by addition of two equivalents of hydrogen in the presence of a transition metal catalyst. The first addition produces a cis-alkene via syn addition, which then undergoes addition to yield the alkane. Notice that we cannot stop with the cis-alkene, it will go all the way to the alkane. Alkyne to alkene. A deactivated or poison catalyst can be used to stop the reaction at the cis-alkene without further reduction. If we have a poison catalyst, we can stop here at the cis-alkene. It will not continue on to the alkane. One way to do this is to use Lindlar's catalyst, and P2, a nickel-boron complex, these tend to be the common example of poison catalysts. Lindlar's catalyst looks like this. We have quinoline, palladium barium sulfate, and methanol. We can have dissolving metal reduction. This reduces an alkyne to a transalkene using sodium metal and ammonia. Here's sodium metal and ammonia resulting in the transalkene. This reaction is stereoselective for the anti-addition of H and H. Proposed mechanism. Dissolving metal reduction reduces an alkyne to a transalkene using sodium metal and ammonia. The proposed mechanism is shown here below. The first step is the nucleophilic attack. The sodium atom transfers an electron to the alkyne, forming a radical intermediate. Note the use of fish-hook arrows to show single electron movement. The paired electrons and the single electron adopt an anti-geometry. Note that the anti-geometry would allow it to obtain a lower energy, therefore be more stable, than a higher energy where we would have repulsions between the lone pair and the radical. Steps 2 and 3 are proton transfer and nucleophilic attack. And then step 4 is another proton transfer, resulting in the transalkene. Reduction summary. Know the reagents needed to reduce an alkyne to an alkane, a cis-alkene, and a transalkene. To obtain a cis-alkene, one will use Lindlar's catalyst and hydrogen gas. To obtain a transalkene, one would use sodium metal and ammonia. And to obtain the alkane, we can use hydrogen gas over platinum in any of these scenarios. Hydrohalogenation affords Markovnikov addition of H and X to an alkyne, which is the same as with an alkene. So an addition of HX to an alkene results in a haloalkane. We can do the same to an alkyne, and that will result then in a haloalkene. Excess HX will then afford a geminal dihalide. A geminal dihalide means that we have the halogen added to the same carbon that used to be, in this case, sp hybridized, then becomes sp3 hybridized. What is the mechanism? If the mechanism was analogous to HX addition to an alkene, it would require the formation of a vinyl carbocation, because the proton transfer to the alkyne will result in a positive charge on a sp2 hybridized carbon, which would then undergo, in theory, a nucleophilic attack. But vinyl carbocations are extremely unstable, so this mechanism is pretty unlikely. Kinetic data also suggests a different mechanism is in play. Kinetic studies suggest that the rate law is first order with respect to the alkyne and second order with respect to HX. The mechanism must be considered with a termolecular process. The proposed mechanism, therefore, is that two alkyl halides are undergoing attack and attacking at the same time in this transition state here and resulting in this haloalkene. It is possible several competing mechanisms are occurring. Anti-Markovnikov hydrohalogenation. HBr with peroxides does promote anti-Markovnikov addition, just like with alkenes. If we have HBr peroxides, we will get a mixture of E and Z isomers with this alkyne. We will obtain the anti-Markovnikov addition. It only works with HBr though, not HCl or HI. This is undergoing a radical mechanism that we will cover later. Hydration. Alkynes can also undergo acid-catalyzed Markovnikov hydration. The process is generally catalyzed with mercury 2 sulfate to compensate for the slow reaction rate that results from the formation of the vinylic carbocation. So it's not just sulfuric acid and water that's required, but also mercury 2 sulfate. The mechanism of hydration. The alkyne attacks the mercury cation to form the mercurium ion intermediate, which is then attacked by water, which is then followed by deprotonation. A proton then replaces that mercury 2 species to form an enol intermediate. So we have a proton replacing eventually that mercury 2. Mercury 2 is lost, and we have the enol intermediate. This means that we have both an alkene and an alcohol group attached to the vinylic carbon. The enol itself tautomerizes to the ketone. The process is called keto-enol tautomerization. That just means it goes between the two species, between the enol form and the ketone form, via a process of proton transfers. The enol and the ketone are tautomers of one another, and equilibrium generally favors the ketone. Hydroboration oxidation of alkynes is the same as for alkenes. It is regional selective for anti-Markovnikov addition, which means HOH will add across the triple bond anti-Markovnikov. The OH will go to the carbon with the less carbons, or the more H's. It also produces an enol that tautomerizes to the aldehyde. So just like the previous example, the enol tautomerizes or changes to the aldehyde. In this case, tautomerization is base catalyzed. There is going to be a proton abstraction by the base, resulting in this oxide ion. The electrons get pushed down, and the pi electrons become lone pair electrons in the resonance structures. The lone pair electrons attack a proton, and we end up with the aldehyde species. The aldehyde is a more stable of the two. We compare the enol to the aldehyde. Modified borane reagent to aldehyde. If BH3 is used, then the alkyne can undergo two successive additions and result in undesired products like we see here. To prevent the second addition, a dialkylborane is used instead of BH3. The bulky alkyl groups provide the steric hindrance to prevent the second addition, and there's only one addition that occurs. The modified borane reagent allows for the conversion of a terminal alkyne to the corresponding aldehyde without furthering the additions. For example, here we have this alkyne. With the reagents, we're using a modified borane, which will result in the aldehyde. The terminal alkyne. For terminal alkynes, Markovnikov hydration will yield a ketone. So here's our terminal alkyne, Markovnikov addition. It's using water and sulfuric acid, but don't forget that mercury 2 sulfate catalyst is also needed. For anti-Markovnikov hydration, it's going to yield an aldehyde. So if we use something like a modified borane and then follow that up with sodium hydroxide and hydrogen peroxide, we end up with the anti-Markovnikov addition, which results in an aldehyde. Halogenation. Halogenation of alkynes yields a tetrahalide. If we have excess halogen in an inert solvent, a alkyne can be converted into a tetrahalide. Two equivalents of halogen are added with excess X2. When one equivalent of halogen is added to the alkyne, we get both the anti and the syn products, where we have the anti as major and the syn as minor. The mechanism for alkyne halogenation is not fully understood. If it is like halogenation of an alkene, only the anti-product would be obtained. Ozonolysis. Ozonolysis of an internal alkyne will produce two carboxylic acids. We have an internal alkyne. Ozone followed by water will result in the cleavage here between the two carbons and the production of two carboxylic acids. Ozonolysis of a symmetrical alkyne is particularly useful to prepare carboxylic acids. Only one product is formed and two equivalents of it. Ozonolysis of a terminal alkyne yields a carboxylic acid and carbon dioxide. Note that this carbon here will make the carboxylic acid, and the carbon that's terminal of the alkyne will produce the carbon dioxide. Predict the products for the following reaction. Go ahead and predict the products, and then we'll check. Hopefully we can all agree that here is a C triple bond C. We're going to have cleavage here in the formation of two carboxylic acids. Alkylation of terminal alkenes. Recall that terminal alkynes are completely converted to an alkyl ion with sodium amide, where the amide is a very strong base and it can remove H+ from a terminal alkyne, resulting in an alkylate ion. Alkylate ions are good nucleophiles. SN2 reactions will occur with alkyl halides. We're able to see then the formation of new C bonds whenever we have the alkylate ion and alkyl halide. A reaction will take place via SN2. Mechanism SN2. Alkylation of the alkylate ion is SN2 substitution, and so it works best with methyl and primary halides. Elimination via E2 dominates with secondary and tertiary halides. Acetylene can actually undergo two successive alkylations because it has two carbons that are terminal. It's the simplest alkyne. This must happen in steps. Complex target molecules can then be made by building a carbon skeleton and then converting the functional groups. 4. Synthesis of alkynes. Like alkenes, alkynes can also be prepared by elimination. If we have a strong base, from an alkyl halide we will get a alkene. If we have an alkyl dihalide and a strong base, that will result in a alkyne. So we need a dihalide to make an alkyne. Such eliminations usually occur via E2 mechanism, and we may use either geminal or vicinal dihalides. If we have a geminal dihalide, that means we have on the same carbon two halogens, and that will end up resulting it after two sequential E2 reactions into an internal alkyne. If we have vicinal dihalide, that means we have on adjacent carbons halogens. Under the presence of a strong base, we will also get the alkyne. Prep using excess sodium amide. Excess equivalents of sodium amide are used to shift the equilibrium towards the elimination products. So here is excess sodium amide, which will result in the alkylate ion. Aqueous workup is then needed to produce the neutral alkyne. Note that once the alkylate ion is produced, then in order to protonate it, we can use something like water. We would end up with the weaker acid being the terminal alkyne and the weaker base being hydroxide. Overall, a terminal alkyne is prepared by treating the dihalite with excess sodium amide followed by water, and it must be done in steps. Complementary reactions. Hydrohalogenation of alkynes and elimination of dihalides represent complementary reactions. So we noted that we can take an alkyne, excess HX, and get the dihalide. We can take the dihalide, excess sodium amide and ammonia, followed by water, we get back the alkyne. 5. Synthetic strategies. Recall the methods for converting triple bonds to double or single bonds. An alkyne can be converted directly to an alkane through the use of hydrogen over a platinum catalyst, or it can be converted to an alkene, a cis-alkene using Lennard's catalyst and hydrogen, or a trans-alkene using sodium and ammonia. The alkene itself can be converted to an alkane by using hydrogen and platinum. But what if we want to reverse the process or decrease saturation? Halogenation of an alkene followed by elimination will yield an alkyne. So if we have an alkene and add bromine across a double bond, we will have a dihalide which can then be converted to an alkyne with excess sodium amide and then followed up with water. These reactions will give us a handle on interconverting single, double, and triple bonds. Therefore, we can go in either direction now. We can go from an alkyne to all the way down to an alkane, or vice versa, an alkane all the way to an alkyne. Key alkyne reactions. 1. Elimination. 2. Hydrohalogenation, but we need 2 equivalents. 3. Hydrohalogenation with 1 equivalent. 4. Acid catalyzed hydration. 5. Hydroboration oxidation. 6. Halogenation with 1 equivalent. Halogenation with 2 equivalents for 7. 8. Ozonolysis. 9. Alkylation. 10. Dissolving metal reduction. 11. Hydrogenation. 12. Hydrogenation with a poisoned catalyst. Now to visualize those key reactions. If we note here in the middle, this is our alkyne, and reactions 1 through 12 are the ones that it can undergo. And note, it can also go in opposite directions depending on what reagents are used. We can go back to the alkyne depending on, are we using a dihalide and excess sodium amide followed by treatment with water, we'll get the alkyne back. But the alkyne itself, if we have excess HX, can undergo the formation of a vicinal dihalide. Make sure that we know all of these reactions that an alkyne can undergo or how it can be produced.